So part 4, I'd like to share some exemplar with you about sustainable aviation fuels and what it's possible to simulate with AMR codes in terms of near DNS. I would still say this is an implicit LES because we're not resolving all the way down. So we had the good fortune of using the Paley LMX LOMOC adaptive mesh refinement code to simulate an aero-engine combustor. This is the Cambridge burner, the so-called swirl-stabilized spray combustion burner that's been run by Nandis Masterakos at Cambridge in conjunction with some of the Rolls-Royce collaborations. So the work here is really done by my postdoc, Bruno Soriano, and sponsored by the Department of Energy's Vehicle Technologies Office Sustainable Aviation Fuel Program. So as you know, there is a wide range of SAF properties of varying both chemical as well as physical properties for the different derived cetane numbers, telling you how ignitable a fuel is, as well as physical properties on boiling points and volatilities for the spray. And all of these different SAFs that are being considered can impact mixture preparation, combustion dynamics, and emissions. And so, and because SAF production is so low right now, its availability is very, it's hard to get a hold of SAF, small amounts of SAF. And so doing experiments or large rig tests is very difficult. And so increasingly we're trying to rely on computation and hopefully the generation of predictive, computationally efficient models that we could use in RANS or LES, subgrid scale models, to test in, various combinations, fuel blends of these alternative SAF fuels in CFD to help reduce the cost of testing. And so using high-fidelity DNS or near DNS kinds of simulations can shed light on some of this complicated combustion phenomena and help improve these models. Another important aspect is that soot emissions from aircraft need further investigation when you have different SAF fuels for their propensity to form soot, because the particles that exit the aircraft and their size distributions and morphologies determines how ice crystals are nucleated downstream and form contrails that add to the radiative forcing of our climate. And so some of the modeling requirements are, in addition to gas phase kinetics, this problem is highly multi-physics. You need to be able to predict multi-phase combustion, so spray evaporation and mixture formation, and also the combustion, especially for the conditions of lean blow-off or high-altitude relight or for cold start, can entail multi-modal combustion. So it may not just be non-premixed combustion or premixed combustion, but it could be a mix of partially premixed, non-premixed everywhere. So the models would have to be able to predict that kind of behavior when you push in these rate limiting operating conditions. And also we need soot models that can be incorporated in CFD calculations. So as I already mentioned, the purpose of our calculations is to leverage DNS to help to provide data for improving combustion models. And I think I've already mentioned this. Some of the conditions we're testing are near lean blow-off conditions, and prior to lean blow-off occurring, you might have substantial amounts of localized extinction and reignition under these adverse conditions, and depending on which fuel, alternative fuel, SAF fuel you're using, you could see more or less localized extinction, and it may be more resilient to lean blow-off. The National Jet Fuel Program in the US has looked at lean blow-off sensitivity, which is plotted in this image on the right. And it shows the lean blow-off tests from various experiments and the sensitivity of the lean blow-off to the derived cetane number for different fuels and for different combustors. So the derived cetane number is a measure of the ignition quality of a given fuel. Oops. And what we see in this plot then is for low derived cetane number, the sensitivity is very high. And it's thought that the ignition quality then is directly correlated with lean for lean blow-off. And so if you have SAF fuels like alcohol to jet or C1 as a representative low derived DCN fuel, we'd like to study its dynamics near lean blow-off compared to the conventional jet fuel, Jet A. And so anyway, we hope DNS can provide useful information to help understand flame stabilization near lean blow-off. And then this would help assist in the development of flamelet models that can operate under these highly mixed mode regimes. So the first part of my talk here is going to focus on flame stabilization. And then towards the end, I will touch upon what happens when you generate gas expansion at the flame scales due to heat release rate, especially in conditions near lean blow-off, where you have lots of extinction and reignition happening locally. That could lead to an inverse cascade. The conventional wisdom is that the turbulent kinetic energy moves in the forward direction from the large scales to the small scales where viscosity dissipates the kinetic energy. But there could be possibility under these lean blow-off conditions where you could have energy produced at the fine scales that could lead to backscatter. And that would, of course, have to be considered, which is in things like large eddy simulation, which usually don't account for which only account for the forward direction. Okay, so as I said, we performed DNS of a multi-phase swirl-stabilized lab-scale combustor from Cambridge. The experiment conducted there. And this is the configuration shown on the left. So it has a bluff body geometry. And we performed calculations using the Lomoc solver with the Peli suite of Peli LMX code, and including the spray model in that calculation. And also, we've just started to include the soot model that was developed at Princeton by Michael Mueller, which is the hybrid method of moments. And we're trying to improve its accuracy by going to a sectional model that Michael's developed. This is the Peli LMX computational domain. And you can see it's pretty big. It's 160 millimeters in the axial extent and 80 millimeters in the radial extent. And I'm just showing, I think Bruno is plotting the heat release rate, and the little white dots represent the liquid phase. The image on the left is our initial attempt at using hybrid method of moments to get the soot volume fraction, which is the isocontours are shown there. And I'll be talking about two fuels today. We'll be comparing the alcohol to jet C1 low cetane number fuel compared with Jet A, which is a conventional jet fuel. Okay, so as I already said, we included the thermokinetic library for Peli physics, for chemistry, thermodynamics, and the multi-physics library called Peli MP for spray, soot, and radiation. All of these tools for Peli and the various libraries are available openly, and they're located out on GitHub. So if any of you guys want to download and try it, and there's examples there, you're welcome to have a look. The code features adaptive mesh refinement, and it was, as I mentioned in my first lecture yesterday, that it supports modern heterogeneous exascale computers with lots of GPUs. And it has treatment for embedded boundaries and cut cells so that we can handle a little bit more complex geometry like this swirl-stabilized bluff-body burner. The targeted fuels are Jet A, which contains 58 species using a reduced mechanism, reduced by Tong-Hung Lee's group at University of Illinois. And then C1, ATJ, which has 60 species, also reduced by the same group. And then they've been working on adding soot modeling to these two fuels. And as I said earlier, the soot model that we're currently using in Paley LMX is the hybrid method of moments, where the soot precursor is naphthalene, or A2. The conditions for the experiment are described in a paper in Fuel by El Helou, where the bulk velocity of the fuel is 16 meters a second. And then we get the swirl inflow velocity by running auxiliary LES simulations using Converge, and then that's fed into to this computation. We add on top of the inflow velocity a zero mean velocity fluctuation. That's about 10% of the bulk velocity. And LT here is the half width of the air passage. Initially, the unburnt airstream temperature is 388 Kelvin, and these experiments were conducted at ambient pressure. Just to give you an idea of the AMR mesh on the bottom right, you can see there's 4 AMR levels. We have the base level plus 3 additional levels of refinement, as shown by the white cross-hatched lines, and then the black finest mesh in the black cross-hatched area. And so with the 4 AMR levels, our finest mesh is about 78 microns. So we have about 1 grid point across, 0.8 grid points across the mean Kolmogorov scale, and maybe about 6 to 7 points across the flame thermal thickness. So the flame, that's a little bit under-resolved, but it's close. The number of cells here is approximately 350 million. And this figure then, so what our objective then is to look at the complex coupling of this complicated flow field in this swirl-stabilized bluff body spray flame. And we're focused on the diffusion flame, combustion, and local extinction occurring, and then reignition of those local extinction regions by either autoignition or edge flame propagation. So these are kind of dynamical events that usually precede lean blow-off. So we're not per se simulating lean blow-off directly with DNS because that's too expensive, but we are looking at some of the conditions that might occur ahead of lean blow-off. This picture here shows the instantaneous field for the Jet A fuel, and it highlights some of the complexities in this combustion process for the swirl-stabilized spray flame. The 2D isocontours in grayish colors show the streamwise velocity, where the air stream is issued at the inlet, and it's accelerated by the restriction in the bluff body region. And what we see are 2 mixing layers or shear layers that are formed after the bluff body exit. You see an outer shear layer that's generated by the interaction of the incoming air with the fluid close to the outer walls. And then we also see another second inner shear layer that's formed by the incoming cold air stream mixing with the high temperature products that's close to the flame stabilization location. So the interaction between the shear layers and the burner geometry generates these 2 different recirculation zones that are labeled by the white lines, the outer recirculation zone, and then the central recirculation zone behind the bluff body. The outer recirculation zone is comprised mainly of hot air that's recirculated from the combustion process occurring in the central recirculation zone. And despite its potential contribution to flame stabilization, similar to a co-flow in a jet flame, we didn't see any flames in the outer recirculation zone at all. On the other hand, liquid fuel is injected into the central recirculation zone. That's denoted by those aqua dots or spheres. And it's injected into the central recirculation zone, which contains combustion products, which quickly vaporize that liquid fuel to form a pocket of rich mixture between the spray cone and the bluff body. And then the rich hot mixture interacts with the incoming fresh air through the inner shear layer to establish a flame there. And high heat release rate is also observed in the central recirculation zone through the recirculation of oxygen, air that didn't interact with the inner mixing layer. What I'll show next is then a bunch of local extinction that occurs that produces a heat release rate field that's disconnected, and it leads to partially reacted mixture that advects both in the streamwise as well as in the azimuthal directions. And so this increased level of extinction phenomenon has been shown to be a key precursor to lean blow-off. And so therefore we're going to drill in and look at the details of local extinction and reignition for this flow configuration. So this is just a center plane cut through the instantaneous heat release rate field. And what I'm showing here is the stoichiometric mixture fraction line. This is the white line in the image. And there are several features that I want to show that exist at any given time. And so we see regions that are locally quenched, labeled as extinction. So there's discontinuities, disconnected heat release layers. We see lots of diffusion flame combustion going on. And then we also see some evidence of triple flames. So you can see where I labeled them as edge flames, where they have brighter, almost whitish, the leading premixed, lean and rich premixed flames, and then followed by a trailing diffusion flame. So this is the instantaneous picture and sample of what you might expect to see near lean blow-off in the near field region. And just to introduce you to triple flames, I've drawn a cartoon. Well, actually, this is taken from an earlier paper, that we wrote, and it shows the different structures of an edge flame or triple flame, which is comprised of a premixed leading edge that's fuel rich on one side of the stoichiometric mixture fraction and fuel lean on the other side. And then behind that is the much weaker burning trailing diffusion flame. And so the relevant quantities here would be the stoichiometric mixture fraction isosurface, which is denoted by the black solid line, and then some progress variable like 0.8 that would measure the location of the edge flame. Because later we'll use that definition to help determine how fast that edge flame's propagating. Okay, so here to quantify ignition and deflagration kinds of events for Jet A and C1 fuels, we can define a Domkohler number, which is the progress variable, which is based on the ratio of the reaction rate of the progress variable to its diffusive flux, diffusion component. And it's been shown before that Domkohler number typically around 3 or 4. If it's greater than that, it is indicative of the greater significance of reaction rate compared to diffusion and representative of autoignition, whereas if dA is less than that value, it's diffusion limited, and so it's more representative of a diffusion flame or premixed flame. And so we can see in these images here that there are both deflagration and ignition fronts that coexist throughout the flame, throughout this, throughout the burner. And on the left image, we see what I'm plotting here are maps of dumb color number, where the yellow line corresponds to heat release rate above a certain threshold, and then the dashed white line is the stoichiometric mixture fraction. And so we can see that the blue regions correspond to low Dom color number, red corresponds to high Dom color number. And so there are regions where we see low Dom color number in the left plot, especially in the inner shear layer. In another region near the central recirculation zone, where the fuel's being injected, we see flame propagation into a high Dom color number region. So this is limited by diffusion. Those are the red isocontours. And then for the C1 fuel, so the bottom two images are for Jet A, and for C1 in the upper right, we see flame propagation into a low Dom color number region, predominantly just deflagration. And so while you do see some evidence of deflagration propagation into assisted ignition, or assisted propagation assisted by autoignition, and some autoignition regions for Jet A, it is predominantly just flame propagation that we see at lower Dom color numbers when we go to a low-derived cetane fuel like C1. If we aggregate the statistics, I should say we define the progress variable here based on, we've tried it for several definitions. One, based on the CO2 plus CO. We've also defined it before based on CO2 plus CO plus water plus H2. And again, DA slightly above 3 or 4, here 4, denotes ignition, less than that is deflagration. And so if we look at the percentage of the total heat release that is contributed by deflagration versus ignition based on this criteria for the two fuels, C1 and Jet A, they more or less look the same. So most of the heat release rate is coming from premixed flame propagation, deflagration, rather than autoignition for both fuels. Beyond that, then we can try to distinguish whether we've got premixed flame propagation or diffusion flames contributing to the heat release rate. And the way we do that is we compute the normalized flame index, the so-called Takano index, which looks at the gradient, the alignment of the gradient of the fuel and oxidant where the normalized, and we see that the normalized flame index is close to unity when you have premixed flame and close to -1 when it's non-premixed. And I should say this fuel, these jet fuels are really complicated because they're not, when it encounters hot product gases that are a little bit over 1,000 degrees Kelvin, as it does in the central recirculation zone, it pyrolyzes. And so the flames that we see that are running around and getting quenched and reigniting is usually not the original fuel. It's not the C1 or Jet A fuel, but it's the pyrolyzed fuel fragments that that actually are these subsequent flames that burn. So that's a complication, is how, depending on how hot it is locally, your mix of fuel fragments can change. On the backside of this problem, it's also very complicated because once you quench a flame locally and you're mixing some diluted hot products in there, those start to cook also depending on how much residence time you allow it. And so in the quenched regions, you also have reactive intermediates and maybe even cool flame ignition types of species into which these triple flames or edge flames are propagating. And so it's not just an ordinary flame. It's on one side, it's pyrolyzed, and on the other side, it can either burn into inert fuel or fuel fragment, or it can burn into something that is reactive and partially oxidized. And so it's quite complicated. But nonetheless, we try to look at the percentage of total heat release rate that's burning in a premixed mode. Oh, I should say the the normalized flame index is insufficient to tell you whether it's premixed or non-premixed flames. It just tells you the mixing direction, right? And then you have to condition that further on some threshold value of heat release rate. So if it's not burning, it's not a flame. So you condition it on heat release rate above a certain threshold. And then we had the fun of trying to define, well, which fuel fragment are we going to use to measure these gradients? So we tried a bunch of them. And we tried, I think the one we came up with that seemed most reasonable was C2H4. We also tried C2H2. The soup goes on. I don't think I have that slide here, but there's quite a number of different fuel fragments, and they're not necessarily all aligned, which makes it more complicated. But we used ethylene, and when we used ethylene, we found that that for the lion's share of combustion of the heat release rate, I should say, is coming from premixed combustion. These are the blue bars. And only a small amount is coming from non-premixed combustion. And so you might ask why, and I'll try to go into that next. And so when we look at just the instantaneous behavior for Jet A and C1, top row and bottom row, we see, again, the structure that I already described. For temperature, OH, mixture fraction, and streamwise velocity going from left to right for the two fuels. And you see from the OH contours and also from the temperature contours where there's localized extinguished regions. And you can also see where, from the mixture fraction, that in the inner shear layer where you have fuel-rich pyrolyzed intermediates or reactants. So we also see evidence from these isocontour plots of the stoichiometric mixture fraction colored by heat release rate in the left plot, by temperature in the middle plot, and by an intermediate species, formaldehyde, in the right plot. You can see the boundaries of where local quenching has occurred. So the gray regions in the heat release plot are the quenched regions where the temperature is lower, roughly about 1,000 Kelvin or so, or a little bit higher. High temperature regions are denoted in red. And then where the quenched regions are happening, we see the accumulation and buildup of stable intermediates like formaldehyde. And so if you can imagine some edge flame contour around that extinguished region that's trying to close up that hole. This particular case for Jet A is propagating not into the fuel fragment, original fuel fragment, but rather into a soup that already contains a lot of reactive intermediates, stable intermediates like formaldehyde, HO2, and a whole bunch of other stuff. So what we tried to figure out was then how fast is that hole closed? Are these extinction holes reigniting? And one way to look at this is by computing the propagation speed of that flame edge, which I mentioned earlier is denoted by the intersection of the stoichiometric mixture fraction isosurface and the progress variable isosurface that denotes the maximum heat release rate. And so we can compute the displacement velocity, that's the velocity of the intersection of those fronts relative to in the normal direction relative to the local gas velocity. And in this case, when we have partially premixed combustion at the leading edge or this edge flame, the displacement speed is defined based on both the progress variable, C, as well as based on the mixture fraction, Z. And so we define the displacement speed as a balance based on the progress variable as a balance between reaction, normal diffusion to the isosurface, and tangential diffusion to that isosurface. And then we define the propagation speed of the mixture fraction surface just due to its diffusion, assuming that it's a unity Lewis number diffusion, so there's no additional source terms in the mixture fraction equation. And then to get that intersection correct, the speed of the edge flame then depends not only on the displacement speed of the progress variable and of the mixture fraction, but it's weighted by this variable k, which is the inner product of the normal vectors, a little bit of geometry, normal vectors of the progress variable and mixture fraction isosurfaces. And so if we combine all of that, we get how fast that edge is propagating. So this figure then shows the doubly conditional mean of the Dom color number that I defined earlier at the edge flame location, where high Dom color number is denoted in red, low in blue colors. And red, as you recall, high values give you ignition and low values give you deflagration. And so the conditional mean is conditioned at the edge flame location, the stoichiometric isosurface intersection with the edge flame, with the progress variable. And it's, the conditioning is based on the normalized edge flame speed, SD edge, divided by the laminar flame speed, and the mixture fraction dissipation rate chi sub z on the ordinate. The isolines here, shown in yellow, pink, and black, represent the joint PDF of the edge flame, normalized edge flame speed, and the scalar dissipation rate. And then the mean displacement speed of the edge flame conditioned on mixture fraction dissipation rate is shown by the black solid line. And so overall, from these statistics, we see an overall positive edge flame speed across all of the dissipation rates, which shows that on average, the edge flames are closing or reigniting the flame towards the reactants. And that positive correlation between the scalar dissipation rate and edge speed for high values of dissipation rate is consistent with previous findings for non-premixed jet flames that occur during reignition. But here we have a much more complicated flow situation. In contrast, the negative values for the edge speed, which is further opening up the extinction holes, it corresponds to an increase in the unburned region of the stoichiometric mixture fraction isosurface, and occurs over a pretty large range of mixture fraction dissipation rates. Regions that are dominated by molecular diffusion, where the Dom color number is low, tend to have low to negative edge flame speeds, whereas more reactive fronts that are supported by ignition, assisted ignition or auto ignition, tend to have higher speeds. And so then if we, let's see. So then if we compare the, oh, I think I've already shown this one, sorry. So the bottom right figure is then if we compare the PDF of the progress variable for the, in the extinguished region between jet A in black and C1 in red, we see that reaction progress is further along, and therefore more evidence of having stable intermediates in the quenched regions when you go to higher derived cetane numbers like jet A compared to C1. And so there's more likelihood of ignition assistance due to deflagration when you have higher cetane fuels like jet A. We also looked at the PDF of the edge flames, normalized edge flame speed then between jet A and C1. And again, we see that for jet A, it tends to have a higher edge flame propagation speed, about 2.5, the peak is at about 2.5 times the laminar burning velocity compared to C1. which is closer to unity. And again, it's because of the higher reactivity and more ignitability of the Jet A fuel compared to C1 that it starts to produce these ignition intermediates when you quench the flame that help the flame propagate at a faster rate to reignite the flame. So what we find, contrary to what some of the experiments that were performed at the National Jet Fuel program found, is that the lean blow-off correlation may actually correlate with the flame speed, the local flame displacement speed, not the laminar burning velocity, but some sort of partially premixed edge flame speed. And so this is something that needs to be looked at a little bit more closely, especially for modeling. So yeah, first we see a cetane number correlation, at least for this representative ATJ with respect to Jet A with lean blow-off, where we see a propensity for premixed edge flame propagation into these more reactive fuels. Okay, so then the last part of this talk, I'd like to talk a little bit about backscatter. So classical theories of turbulence typically suggest that the kinetic energy cascade for non-reacting incompressible flows has a net transfer of energy that's downhill from the large to the smallest scales. However, past studies, reacting flows, as I said earlier, could generate turbulence at the subgrid scale because through gas expansion effects can inject energy in the dissipation part of the spectrum. However, past studies, both DNS work that we did a long time ago, showed that thermal expansion is shown in this red region from the flame. This is a kinetic energy spectrum. And we looked at a detailed balance in spectral space, and we found that there's very strong. If the flame wasn't there, you would just have a cascade from the large scales through the inertial range, k to the minus 5/3 scaling, and then you would have just exponential decay. But there's this noticeable blip that happens in the kinetic energy spectrum at exactly the location of the flame length scales, wave numbers. And that's due to the thermal expansion of the flame. And if we look at a budget equation for either the scalar variance or the kinetic energy, we find that the source of that generation of gas thermal expansion is due to pressure gradient velocity fluctuations or dilatation fluctuations that are a result of the flame. And the analogy to that for reactive scalars is that you have the reaction rate term multiplied by the mass fraction fluctuations are the source of generation of scalar variance at the subgrid scale. And so the question is, if you generate that, or if you modify or generate turbulence at the subgrid scale, is there any backscatter? Does it just flow downhill, or what is the effect of that on the cascade? And so Adam Steinberg made some measurements in an experiment of a swirl-stabilized premixed burner that's shown in the middle plot in the bottom. And they did instantaneous measurements of both the forward and reverse kinetic energy transfer. And he did it for a reacting case in that configuration as well as non-reacting. And what he found is that forward-reverse energy transfer exists in the flame front, where the backscatter component of that transfer is denoted in red, and blue denotes the forward transfer. And so if you plot that function in the right plot, conditioned on the progress variable, you see that the forward-reverse energy transfer parameter has both components, both in both directions, where negative values of this parameter denote the forward cascade, and positive values denote backscatter. So the basic question is that I wanted to address is that when you have a lot of extinction near lean blow-off, as we saw, we think that these edge flames are present And I didn't mention earlier, but in an edge flame structure, the predominant heat release is coming from the premixed leading edge, and the trailing diffusion generates very little heat release. So there's almost a 10-to-1 ratio in the amount of heat release that's produced from the leading premixed flame. And so the question is, does that make a difference for inducing backscatter near lean blow-off conditions? So we took the DNS of the Cambridge burner and we spatially filtered the data with a Favre filtering operation for a bunch of different time snapshots, because this flame is stationary both in time and as well as in the azimuthal direction. We used a top hat filter kernel where the filter size that we took so far is it's pretty small. It's about 2 times the thermal thickness. Bruno's been looking at various filter sizes now. And we performed the analysis so far only on Jet A simulation. We will also do this for C1. And we presented the data in terms of conditional means as a function of progress variable for 3 equivalence ratio isosurfaces near stoichiometric. So this is what we see. The plot on the right shows the conditional mean of the kinetic energy flux across the filter scale as a function of the progress variable for 3 mixture fraction surfaces, 0.8 stoichiometric through 1.0, through the stoichiometric isosurface from blue to black lines, and they all qualitatively behave in the same way. And so forward scatter in this parameter alpha sub S of S, as defined here, shows that you get negative values when you have forward scattering and positive values when you have backscatter. So we do see evidence of backscatter in the flame zone, particularly in progress variable injection of energy from the flame at the resolved scales for progress variable ranges between 0.3 and 0.6. And furthermore, we see that the correlation between this kinetic energy flux across the filter scale, alpha sub S of S, and dilatation, which is what I just brought up, the divergence of the velocity field due to strong gas expansion caused by this premixed leading edge flame, are highly correlated, especially in the range between 0.3 and 0.6 of the progress variable. And so this suggests that we need some more work on closure models for LES of turbulent combustion near lean blow-off to be able to capture this backscatter that occurs when you have these local extinction reignition events. So with that, I will stop this section, and then we'll talk in a few minutes about the last section, which is on reduced order modeling and a public repository to share DNS data for machine learning training.